Okay, so we had two AP practice problems, and here's kind of the answers worked out so you can use it to study. So this question deals with a rod that's hung at one end and allowed to rotate from horizontal down to hanging vertically. And part A is asking you to show that the moment of inertia of this rod, or the rotational inertia, is ml squared over 3 for the rod of length L and total mass M. So that is L and it's mass M. Okay, so this one is purely a mathematics question, and if you can't do it, you have the answer, ml squared over 3, for the rest of the problem. But you can get a lot of the points for the setup. This is a 3-point section, and only one of them is for actually getting the answer right. So, first thing, we know definitionally our starting point, right? I equals the integral of r squared dm. And so what we need to do, in effect, is we need to take this rod and break it up into lots and lots and lots of tiny little chunks of mass dm. And each of these chunks, right, our pivot point is like right there, that's where it's attached. So each of these chunks is a distance r from the pivot point, right? This one, that first chunk is that far, this one is a different r, this one is a different r yet again. So each of those chunks is a different distance away. And so if we start with this integral, there's a couple things we notice. First, this is essentially a one-dimensional object, right? Where our masses are located are just in sort of this one direction, right? Our horizontal axis, which is x. So we can replace r, the general how far you are from the axis, with x, the horizontal distance. So we aren't moving vertically at all. The second thing is that we're told it's a uniform rod. And so because it's uniform, the fraction of mass, of the total mass, must be equal to the fraction of space, right? How much space it takes up is how much length, out of the total length, right? This is the statement that it's uniform. And that's an important one to remember. So if you remember this uniform statement mathematically, that's a point right there, even if you can't use it in the integral. So let's put that in and see where we're at, those two statements. So x squared, and dm turns into capital M over L dx. Okay. So now we just need to figure out what we're integrating over, right? Clearly it's a distance, but what distance? Well, we start at the pivot point and we keep going until we run out of rod. So this right here, right, is x equals 0, and this point right here is x equals L. And that defines the ends of integration. Right? We need to add up all the mass in the rod from where the rod starts to where the rod ends. And if you get those ends of integration right, that's the second point right there. And so now, if you can solve it, great. That's the third point. But just setting this up right here, right, turning this general expression into something that's actually mathematically solvable is 2/3 of the points. So that's the important thing to be able to do. So if you evaluate this integral, right, we get a mass over length, which is constant from 0 to L of x squared dx, and that turns into x cubed over 3, evaluated at 0 and L, and that is ml cubed over 3L, and so one of those L's will cancel, ml squared over 3, which is what we were asked to show. Okay, so that is part A. The other parts involve now more physics. So, part B, we need to figure out how fast our object is moving when it's rotated to fully vertically. And we kind of just have to assume that the rod is frictionless. because we don't have any knowledge about how much friction is going on. So the best assumption you can make is that there's no friction at the pivot point, and no air resistance and similar things. You can't really do this question with free body diagrams and kinematics, because the force will not, well, the force will be constant, but the torque will not be. As the rod rotates, right, the sine of the angle between the force and the distance to the pivot point will change. So the acceleration, or the angular acceleration, won't be constant. So you really need to do this one with energy conservation. You can mathematically solve it with using forces and then kinematics, but not in ways we've done in class. It's not impossible, just not, it's far harder, first of all. So I'm going to do it with energy conservation. Right, so our rod starts off horizontal, and it ends up vertical. But we know gravity only really cares about the motion of the center of the mass. And since it's a uniform rod, that's the center of the rod, right? So this length, right, this spot right here, I'm going to call y equals 0. And so then this point up here is y equals L over 2, right? That's where it starts, because it's the center mass is the center of the rod. And so we're going to say that energy is conserved. E initial equals E final. Making any statement like that right there, if you just state that energy is conserved and you want to use that somehow, that's 1 point, even if you can't do it correctly. Just noting that energy is conserved. So before, what energy do we have? Well, we don't have any kinetic, it's at rest, but we do have potential. The mass of the rod times g, and how high is it? Well, L over 2. At the end, we've defined that to be our zero gravitational potential energy. So we don't have any of that left, but now we have kinetic. And specifically, we have rotational kinetic, because it's not translating, but it's rotating. And we just found what the moment of inertia was in part A, so let's use that. And we care about the speed, so the linear speed of the end of the rod, which is a distance L from the pivot point, right? So omega is V over L. Okay? So a couple things we can do very quickly. The first, we have an L squared and an L squared, those cancel. We have an M and an M, those cancel. So we clean up all this, we get GL over 2 equals 1/6 V squared. And this is now pretty easy to solve for V, right? So we can cancel this 2 and turn that into a 3 as well. So we get V equals the square root of 3GL, right? All that is under the square root. And so that's part B. And again, if you just noted that this height, right, was the motion of the center of mass, so it was L over 2, not L, that was another point, even if you couldn't solve it correctly. And if you replaced omega with the V divided by the total length L, because you care about the end of the rod, that was another point. There are lots of points for the setup. Okay, now we're moving on to sort of the experimental part of the question. We know what the velocity should be as a function of how long the rod is. So now we're going to test that. They're doing an experiment. They measure how long the rod is and how fast it travels when it's vertically, when it's made to that vertical point. And so there's some data recorded, and your first question that you're asked is, what do we want to plot to get a linear relationship where the slope of that line is related to g? And there's a couple different ways you can come at this. The first way uses what you did in part B, so I'm going to start with that, and I'm going to talk about a bit more of a general way as well. So we want something that's linear. We know what the function looks like for a linear relationship, right? It's y equals mx plus b, right? So we want something that looks like that relates length and velocity. And quite handily, in part B, we found an equation, v equals the square root of 3g square root of L. And so if we recognize that m and the square root of 3g sort of match up, y is one of our sort of data points, matches with v, and x matches up with the square root of L, right? Those things are just kind of, I'm just matching patterns is really the best way to show it. I'm making these equations look the same, right? And this is sort of the correspondence you need to do that. And then B, right, in this case is going to be plus 0. Right? There's no y-intercept value. So if you do this, you recognize that what you should be plotting for a linear plot is going to be V and the square root of L. The other way to do it is think about where this came from. It came from energy conservation. We want one thing related to the gravitational potential energy, right? Which we wrote as mg L over 2. So we want something related to this. It has to be the length, right? Because it has to be one of our data. It's either the length or velocity. We have a length in it. So this would say we want to use length. Then we need something related to the kinetic energy that we think is an equivalent total amount of energy, right? So the kinetic energy, right after we cleaned things up and simplified down, we got it down to 1/6 mv squared. And so once again, we can use either length or velocity to get at what kinetic energy is, and we only have a velocity in it, right? So we see a v squared there. And so this approach would suggest that we would want to plot L and v squared. And so these are your two possible options. You can pick either one. You can either plot this versus this or this versus this. And it comes from how energy is related, right? Kinetic energy depends on velocity squared, but potential energy only depends on the position directly. So that's why it's not just V and L like you're given. So depending on which one of these choose, you either take the velocity data points and square them to fill in your data table and leave the other alone, or you take the length data points and take their square root and leave the other one alone. Either one is completely correct and exactly identical. So as long as you pick that and compute it correctly, you're fine. Okay, so we fill in our table, and now we have to actually make a graph, and we're given a very blank axis because, right, you could have plotted two different things. I'm going to plot the velocity and the square root of length because that one comes directly from the equation in B. I think it's a little bit more obvious. So my graph is going to necessarily be a little bit rough because I don't have the graph paper, but remember, you have precisely labeled sort of values. You have to graph it essentially perfectly. So it says very clearly as well what you need to do. You need to clearly scale and label all the axes. So my horizontal axis is the square root of length, which is units, square root of meters. My vertical axis is velocity. That has units of meters per second. And when I take the square roots of all the length, I see that it goes between 0.5 and 1.2. Rather 1.22. So if I make each of my data points each of my tick marks 0.25, it'll work out pretty nicely. You want to use as much of a space as you can. So 5, 7, 5, 1, 1.25, 1.5. Velocity, right, goes from 2.7 to 6.3. So if I make my data points or my tick marks each 1 and go up from 0 to 7, right, so 0 and 0. 1, 2, 3, 4, 5, 6, 7. So again, you have the actual data or grid there, so yours will be automatically evenly spaced. Mine isn't obviously quite as good. So then all you have to do is you have to put your data on that. Assuming you've calculated it correctly, this part should be sort of elementary. Right, you're just putting your data where it goes. And again, I can't do a great job of that, but right, there's one data point at 0.5 and a little bit less than, actually let me change colors, a little bit less than 3, so like one data point like there or so. A bit less than 0.75, and a bit less than 4, so something like maybe there. Another one at 0.87, which is about midway there, and then a velocity of about 4.5, so something kind of like that. One exactly at 1 and just a little bit above 5, So something like that. 1.1 and a little bit less than 6, so maybe like there. And then 6.3 and 1.22, which is there or so. And so it's roughly linear, even with my kind of crude drawing. And it's also good that you can see it's going to intercept about y equals 0. So then, once you got your data drawn, put a line through it that's as close to going through all of it as you can, and it's nice and straight. Use like an edge of a piece of paper. Obviously I didn't, because I can't really do that on an iPad, but make it as clearly straight as you can. And once you've done that, you've answered the question, right? No matter what your data is, put the best linear line through it, and you'll get the points for doing that best fit line, the straight line that best represents the data. Even if your data is messed up, even if you're calculating the wrong thing, even if you plotted the incorrect stuff, come up with a linear relationship that's as good as you can get. Okay, so now, part E, we need to use that line to determine G. And so the reason I picked this one is this one most directly relates easily to, right, that y equals mx was v equals the square root of 3g square root of L. And so this tells us, right, the slope is the square root of 3g. So we have to measure the slope of this line. Right, so say I pick like this point right there and this point right there, right? I measure delta x and delta y. And this, right, delta y over delta x, exactly whatever you drew on your line, measure from your line. Notice I did not use data points, I used my line. That tells you the slope. But we know that equals the square root of 3g, right? That's our prediction. And so we can solve that g equals m squared over 3. So whatever you measure, this delta y over delta x, it just goes right in there, square it, and then divide by 3. And you should get a number that's that is less than 9. Should be, again, depending on exactly what your value is, it should be something like 8.0 meters per second squared to maybe like 8.4 meters per second squared. Again, there's going to be some variability in that. That's probably, they actually probably would give credit for even a slightly broader range, but somewhere in that range. It's definitely less than 9. And so then part 2 is, well, clearly you didn't get a value of g that's very well measured. How do we fix that? And you have to come up with 2 ways to reduce the value of air resistance. We've talked about sort of what affects that air resistance and drag force, and so your job is to make all those effects smaller. So the first and the most obvious one, the one that everyone I think should get, do the experiment in a vacuum, right? If there isn't any air, there isn't any air resistance. Seems obvious, but obvious is okay. How do you get rid of air resistance? Get rid of the air. The other one, your second choice, is a little bit tougher because you have to know a little bit more about how air resistance works. I think the second most obvious one is you make your rod more aerodynamic, right? This is why, this is like car design stuff, right? Cars are made to have as little air resistance as possible. Their shape is designed to be aerodynamic. If you make your rods more aerodynamic, then air resistance has less of an effect. Another thing you could do is if you make the rod just a little bit smaller, right? We could use, instead of a length of 1/4 of a meter, we could use rods that are 5 to 10 centimeters, right? The smaller the rod, the less air it has to pass through, so the less effective air resistance. And then finally, you could also just make the rod more massive. This doesn't affect air resistance directly, but it makes the gravitational force that you're trying to measure a bigger fraction of the net force on the rod. So you're going to get a value for g that's closer to correct because the net force is closer to being entirely gravity, even though you haven't affected air resistance directly. And so any 2 of those 4, and there's probably others that I didn't think of, but those are, I think, the 4 sort of obvious ones. Any of those would reduce air resistance.